Well, good morning, everyone. We're in the second day of our workshop, and hope that I'm sure you will find the program today very interesting, with a lot of scientific and technological details on our topic, ultra-high temperature thermal energy storage, transfer and conversion. First session of today begins with a talk by Merete Tangstad. She's a professor within material science and engineering at the Norwegian University of Science and Technology, NTNU, and well, she's really an expert in silicon production also for solar cells, ferroalloy production, and she will talk about the ultra-high temperature phase change materials for latent heat storage. Merete.
You let me know when it's 5 minutes left. Okay. So, good morning, ladies and gentlemen, and welcome to the first session of today. I will talk about the phase change material and the properties that we are looking for in the phase change material, or at least from some point of view. And as Carlos said, we are in this project because we have a lot of silicon production in Norway, so that is my main background for this project. So the things that we are going to look at in this presentation is, of course, the energy storage capacity or the latent heat of the materials, the volume change, because we don't want to have too much volume change either, because then the crucible may actually crack, the thermal conductivity, because as we are extracting heat, the heat has to go from the solid-liquid interface through the solid part. So, of course, the thermal conductivity will also be an important thing. Another thing, since this is going to be a system that will last forever and ever, going up and down in temperature, which is actually a very interesting topic, is that we don't want to have a lot of change in the phase change material over time, right? We don't want any gassing, we don't want any slagging, we don't want it to interact with any of the materials in the thermal energy storage system. So this is some of the things that I will discuss today. So this you have seen many times already. So here we have the latent heat versus the melting temperature, and as we have talked about already many times, silicon is a good contender to be a phase change material, as it has a high latent heat, it's very abundant, and it's a mature technology to produce it, so it has a low cost as well. One of the big things about silicon is, of course, that it expands during solidification. So it expands about 10% during solidification, which of course is quite radical. It's also very reactive towards its surrounding, so it will react, all material reacts with everything, actually at high temperatures. So this is something that we have to take into consideration. So the strategy of the Amadeus project has been to use alloys. Alloys is, of course, not one single component, but where you have several components. So what we have been investigating is silicon boron alloys, silicon boron chromium, and silicon boron iron alloys. And the goal is to have preferably, of course, a similar high latent heat, which is the main thing. We want to have a lower volumetric expansion, and we also want to maybe to have a bit lower melting point, as we will have increasingly challenging system with increasingly higher temperature. So, if we have also seen this from Pan yesterday, I think, in the where we are looking at the energy of the material versus the temperature. So this is for typical silicon. So of course the energy in the material will increase when it's in solid state, and we increase the temperature because of the vibrations in the system. And this is dependent on the heat capacity. Then we have the melting, and we have a big change in the energy during melting. And then again, we will have an increasing energy in the system after it has molten, when we are in a liquid state, again dependent on the heat capacity. And one of the important things here is, of course, even though we have seen sensible heat systems as well by Antora yesterday, this part, if we have a lot of solid phase in our material, it will have very small effect on the thermal change. Okay, so we really don't, in our system, we would like to avoid having solid materials in our liquid, right? So, and this is for a pure system, one component system. Of course, if we have an alloy, this will not be the case anymore, necessarily, right? So, if we go back to Chemistry 101, this will be the phases that you will have in a mixed system of A and B. It could be silicon and boron, for example, versus the temperature. So we have a liquid area here. We have the solid area here, where we only have a solid A and B. And then in these areas, we have both a liquid and a solid. So if we want to go directly from a solid to a liquid, the only place we can do this is here. We can go from a liquid to a solid, and that will be at the eutectic composition. So one of the points in Amadeus is to use only eutectic compositions. Because if we are at a non-eutectic composition like here, we will actually have a liquid here, but then we will start to precipitate solids, right? So here we will have some solid, some liquid. If we go to an even lower temperature, we will have more solid and less liquid, which means that when we finally come to the solidification temperature, our phase change material will actually only have 50% liquid left, right? Which means that we only get back 50% of the latent heat. So it means that we don't want to be at a non-eutectic composition, we want to be at a eutectic composition. So that is one of the strategies that we have had in the Amadeus project. So if we look at the eutectic composition, it will typically look like this, where you have a very intermediate structure after it's solidified down here. However, if you're at a non-eutectic composition, it will be like this, where we have a lot of eutectic structure here, but we will have some primary crystallization that has been precipitated here. So actually what we see in the silicon-boron alloy that we have investigated is that it may not follow the thermodynamic databases, or that the thermodynamic databases are not accurate, so we are really not at an eutectic level. So we have to continue to work on that to find the eutectic composition actually. So if we are looking at the silicon-boron system, so this is silicon, this is boron, we have the only eutectic we have here, and this is at atomic percent of boron, this is at weight percent of boron. So we see we have 8 weight percent of boron, atomic percent, which equals to 3 weight percent of boron, will be the eutectic composition. So we have focused a lot on this eutectic composition. So how will the latent heat look like for different amount of borons in our silicon-boron alloy? So here we see the temperature, here we see the enthalpy in the alloy. So the black line here is the pure silicon. So we see the latent heat here. If we are at the eutectic composition, 3% of boron, it will be the green line. So the latent heat here will go from here to here. So that will be the highest latent heat that we will have in this system. Because, for example, if we have 15% of boron, that is the dark blue, we see that the latent heat will be much lower compared to the 3%. So again, it will always be a kind of an advantage to have the eutectic composition, not to have a non-eutectic composition. So, okay, yes. So what has been done previously? So a lot of different people have investigated latent heat for a lot of different type of alloys or ternary alloys. So if we look at the latent heat versus the temperature, we can see that there is everything from 100 to 1000 kilojoules per kilo, but all of this in the high enthalpy area are with quite high amount of silicon. As we know, silicon is a kind of a good thing. However, we can work on even lower temperatures by mixing it with different type of elements, like for example magnesium and aluminium, which are kind of quite challenging in many other ways. For example, magnesium will have a very high vapor pressure, aluminium very reactive again. So there is a lot of kind of different alloys have different challenges. So if we look at our materials, so this is the Joule per gram. So here we have the silicon, silicon boron, silicon chromium boron, and silicon iron boron. And these are both calculated based on thermodynamic data and measured as well. So we see they are quite in good agreement, a bit off with the chromium, but this is a work also in progress. Because again, if you are going to measure the enthalpies, it can't react with anything, right? Because then you will get an off. So, however, here is per gram, per mass unit. However, what we want to look at is per volume unit, because if we are going to have a state, if we are not going to send this into space, like Matthew is, we're actually looking for a system that has a low volume, not necessarily a low weight, right? So we want to have a low volume, so this is more interesting for us. So we see that we are in the same, the chromium alloy will be around the silicon. The iron will be a bit lower, but not very much. So these are the enthalpies on the alloys that we have looked at. So what about, so that was the enthalpies. What about the thermal conductivity? Because again, we said that, okay, when you are partly into the solidification, the heat has to go through the solidified part, through the crucible wall, and then down into the cell, right? Where it's extracted. So we want to have a high thermal conductivity. Well, if we are looking at pure component system, like pure aluminum or pure silicon, when we are mixing it with other elements, the thermal conductivity will go down. So this is, for example, pure silicon with the increasing amount of boron. This is pure aluminum with increasing amount of silicon. So the thermal conductivity will go down as we are mixing it. And it will probably go more down than this as we are getting different phases. So in the alloy. So it will also decrease with temperature. So if we look at the thermal conductivity, this is with pure silicon with increasing amount of boron. So we see that with temperature it goes down. So actually the thermal conductivity in the area where we are interested in is in this area. So in the area of 20 watt per meter Kelvin. And with increasing amount of boron, the lower it is actually. So we have also started to measure the thermal conductivity again because I see a lot of modeled data, and since I'm an experimentalist, I would like to have proof that the modeled equals the right values. So if we look at the silicon, both the modeled and the theoretical, no sorry, the measured and the modeled is quite is in this area. If we are calculating for the chromium, for the iron boron alloy, we see they should be a bit higher. However, we have started to measure this. Again, this is a work in progress because this is very fragile material as it crushes down very easily. So it means that also when we start to make samples of it and cutting it, we can introduce micro cracks which will affect the thermal conductivity. So we need to find out a way to actually measure these alloys a bit better. Another thing when it comes to thermal conductivity, so we said, okay, we want the heat to go through the solid material, through the container wall and down into a cell. So it means also that the transfer or between the phase change material and the crucible is very important. So we need a good wetting in a solid state between the two materials, right? Because otherwise, again, you will lose the thermal conductivity. So that is also dependent on the wetting. So we see here we have an alloy with iron, which is not wetting very well, and this will probably affect the thermal conductivity as well. Here we have silicon boron alloy in silicon nitride crucible, and we see it quite good. And here we have a boron nitride crucible, and we see with the silicon boron alloy, and we see even that we have a cavity under here of gas. So it means this is a CT picture of the sample. So this is also something that needs to be taken into consideration. However, this is in small scale, and when you are getting a bigger scale, will this be a problem? We really don't know yet. And I would guess that maybe this is not a big problem when you have kind of a big crucible like we have in the prototype. But that we need to investigate. So another thing is about the wetting, especially for silicon. Silicon if it wets very well when it's in liquid state, it will have a tendency to creep. It's not very easy to see maybe here, but you can see that the silicon is creeping up on the crucible, and it can actually go over the edge if it's too wetting. So if we look at what is affecting the wetting of silicon, one of the things that is affecting the wetting of pure silicon, this is data for pure silicon, is of course the wetting is dependent on the interfacial tension. And the interfacial tension is dependent on the oxygen pressure in your system. So the oxygen pressure, we can see that this is very low, right? It goes from the 10 to minus 18 to 10 to minus 26. So we are talking about really low oxygen pressures here. And we see that if we are in the high oxygen area, it's a different surface tension. It goes from around 700 to the 10 to minus 26. It's about 840, right? So the interfacial tension, or the surface tension between liquid and gas, will be affected. So if we, for example, are looking at two different systems, like the way we are doing experiments in Trondheim, we are using a lot of carbon in our furnaces, so it means that our oxygen pressure will be determined by the carbon material. So then the oxygen pressure will be like this as a function of temperature. In FRI, they are using tantalum, so it means that they will have a lower oxygen pressure in their furnaces. So we at NTNU will probably be here in the 10 to minus 18 oxygen area, and with the tantalum, it will be around 10 to minus 24. Okay, so it will affect the wetting a bit. However, if we are looking at the wetting angle which we see here, of course, if it's very low, you have a very good wetting. So if you have a low or a very good wetting, we see that it will be a bit difference between this 840 millinewton per meter and 700 line. However, not dramatically, or also in the other area. So it will be a bit different, but not have a very big effect. However, the oxygen pressure will maybe have a more important effect on the skin oxide layer. So if we have a substrate here and we have a drop of our phase change material, we will we may have a skin oxide layer. And this is very typical for silicon and aluminium. And this is very, very thin, so it's very hard to detect it. Okay? So again, if we look at the oxygen pressure versus the temperature, it's lost here, but it's pure silicon, and then it's this iron silicon alloy. So we see they are in the same area, or it's actually one magnitude difference between them. So if we are in this area, we will have a skin oxide layer. If we are in this area, we will not have a skin oxide layer, which means that it will affect, you will have lower wettability in this area compared to this area. So it's just a kind of something to be aware of, what kind of oxygen pressure there is in the different type of thermal energy storage systems. So, thermal expansion. When we are looking at thermal expansion, again, very basic figures. So most materials in the world today, if we look at a specific volume as a function of temperature, it will increase as you go up in temperature. Then the volume will increase as you melt it down, and then the liquid, as you continue to increase the temperature in the liquid, will again increase. So most of the materials in the world are according to this graph. However, we have silicon is one exception from the rule, right? So silicon will go like this. So again, if we have a liquid going down in temperature, it will go down. However, the solid phase will have a higher volume compared to the liquid phase. So it means that the silicon will expand about 10 to 11% during solidification. Another example is, of course, water. So it means that ice will always be on top of the liquid water, right? Which is, of course, a very good thing in Norway and other Nordic countries, because all the biology would be dead in the water, right? if the ice were from the bottom. So it's a very good thing for mankind that the water is also one of the exceptions from the rule. Okay, digression. Okay, so what will happen to the thermal expansion? So for most materials, so if you go down in temperatures during this way, the liquid metal will, for most materials, it will start to decrease in size as you solidify it, either from the sides or from the bottom. So you will typically get a cavity formation like this. However, for silicon, it means that it's actually expanding. So it will typically give this hump during solidification. And of course, you will also have a lot of stress on your crucible. So it means that we want to find an alloy which has a low or about 0 volume expansion during solidification, because we are not really looking for this either, with a lot of, and it can also produce a lot of pores up here, right? So we are really looking for something that keeps the delta V about 0. And when I'm talking about delta V here, it's not the propulsion that Matthew talked about yesterday, but it's the volume exchange. So we see here the different compositions. Some of the what we have investigated is with boron, it's with chromium, iron. We didn't investigate anything with copper or nickel. So all of these are theoretically eutectic composition. So we see that silicon with this 3% of boron will be around 10% change, increase in volume during solidification. However, both chromium and specifically iron is only around 1%, so it will keep about the same volume also as copper. So this one is a very good candidate to be a phase change material. So another thing is gases. Okay, so we said, I mean, one of the kind of thermodynamic principles about everything is that if you are in thermodynamic equilibrium, all elements will be distributed in all phases, also in the gas phase, right? So if you look at, if we are at high temperature, you will always have a gas pressure, and that could be, of course, very low. So we can see here, we are talking about 10 to minus 10 or 10 to minus 4th partial pressure of the different gases. If we have silicon and we have some oxygen present, we may produce some SiO gas. Okay, and this is the one that will, if we have any oxygen present in our system, we can, at, for example, say 1300 degrees C, we will have about a bit less than 1% of SiO gas, and that is a bit. We see copper has a bit lower, but still, and then iron, nickel, boron, silicon as such are quite low partial pressure. And maybe it's not a problem that you will have a gas pressure of it, but the problem could be if you have a big variation of temperatures in your system, right? So if you, for example, have some cold materials, it will condense on the cold materials, right? So even if you have very small amount, it may kind of be contribute to problems in your thermal energy storage system. Another example is here we are making some this iron alloy into the crucible or the prototype crucible, and we also did some cycling of this material. And what we want to see after some cycles is that it looks like a nice eutectic structure, that it hasn't changed the composition over time. However, if it's reacting with the equipment, for example, here in one experiment, we had some polluting carbon, probably some dust falling into it. So we see that we get a lot of silicon carbide. The carbon will transform to silicon carbide. The boron in the alloy will react with carbon to boron carbide. So the light gray is silicon carbide, the black is boron carbide. And this will be solid all the time. And of course, it's not kind of a go, no-go situation, but it will reduce the enthalpy change that you will have because you have more solid material again in your alloy. Right? So, finally, a summary of the presentation. So, we have investigated mainly 3 different alloys, silicon boron with different amount of boron. However, our favorite one is the eutectic alloy with about 3 weight % of boron. It should be 1385 here. And it has a good option as a phase change material. It has a high energy storage capacity in joules per gram. However, the problem is the high volume expansion during solidification and also the high capacity for SiO vaporization, because the activity of silicon is quite high. Maybe our favorite for now is the iron silicon boron alloy, which has a bit lower eutectic temperature, so it will solidify around 1200. This is the theoretical, this is what we measure. So it's a good option for the phase change material. It has a slightly lower energy storage capacity, however, not very much, still quite good. However, the volume change is around 0, so that is a good thing, and it also have a quite low SiO and SiO2 formation capacity. Actually, maybe it has a low of this, because this one is a bit higher. So it has been a very good thing so far. We started to investigate the silicon chromium boron alloy, which has the same melting point or the solidification point as a liquid silicon, but only did some preliminary experiments there. And in theory, it has a high energy storage capacity, so that is a good thing. It has quite a low volume change, and it has a high thermal conductivity, so it could also be something to further investigate. However, we got quite a lot of pores in this sample, so we didn't go on with this further. So that was everything that I had. Thank you very much.
Thank you very much, Merete, and the paper is open for discussion. Any questions, comments?
Yeah.
Thank you. That was a very interesting presentation. So I had one question about the inclusion of boron in all of these alloys, because it's obviously extremely expensive compared to these other materials. Like, I think maybe 1,000 orders of magnitude, 3 orders of magnitude more expensive. So I was just wondering, it seems like one of the big issues is the expansion of the silicon during freezing, especially with the cycling. And just the combination of silicon and iron could account for that, because I know they kind of have the opposite effect. So I was just wondering whether you've considered just that, or if you see boron coming down in price in the future, or some other way to integrate that.
I have actually done some experiments with silicon iron only as well. Yeah. So it is a possible material, and maybe slightly lower enthalpy change. However, we also see that the boron seems to suppress some of the oxidation of the alloy, even with 3%. So I think that is kind of an optimality procedure we have to do based on cost and the effects of the different. Because boron will also affect the volume, but I mean, you could use other materials, cheap materials for that, right?
Right.
Yeah. So I think it must be kind of a final evaluation afterwards.
Thank you.
Thank you very much for your nice presentation. I was wondering if there would be any issue with the interfacial thermal resistance between the silicon and the crucible, depending on the pressure because of thermal expansion.
Yes, we would think it would be, right? So, but I think kind of now I would rather have from the thermal expansion, it would actually improve the pressure, which would increase the thermal conductivity, right? However, I think when you have kind of kilos of this material instead of grams, I think actually the pressure would be enough. So I think I would kind of prefer not to have any volume expansion, because again, you know, breakage of the crucible is not a fun thing. This is supposed to last forever. So I think you know, the risk is higher than the gain.
Thank you, Merete. Very nice presentation. Why the weighting is important in the Amadeus project? The weighting that you...
The wetting?
Yes.
Yes. Well, it's two things. And one of the things is that usually if you have a lot of wetting, it can be it can react more, right? So we don't want to have... well, that is actually, I guess Natalia is going to talk about this in the next presentation. So it's about interaction with the crucible, right? So typically, if you have very good wetting, it could be more reactive. It could react more to the crucible, which could be both a positive thing for carbon and a negative thing for other elements, right? So that is one of the things that we have focused on that. But and also, of course, we don't want it to creep out of the crucible, right?
But really, in the Amadeus project, you don't change the phase, no? You are always in the same solid phase.
No, we are going to liquid and solid.
Yes, but
yes.
in the middle.
Yes, but still, if you are in the liquid, it may go over. Okay, so if you don't have this oxide, which we think it is, it's this oxide phase, for example, with graphite, it could kind of go over. Okay, so we have seen that in many experiments. However, how that will also be in a larger scale, right, is a thing that we haven't discussed so much. Because things will be different if you have small samples in the crucible versus a big sample in the crucible, because we can see big difference in how far up the silicon will creep on the walls, for example. If you have a big crucible versus a small crucible, or a big weight versus a small weight.
Very nice presentation. Well done. Several questions. You analyzed the thermal expansion on solidification. Have you analyzed the thermal expansion on the other way, from solid to liquid?
What we are doing, which is kind of it's not purely scientific, because if you had a really round sphere, as we would have in space, for example, you could calculate the going from solid to a liquid much better. But we are just showing it, we are calculating it based on the wetting experiments. Then you can see the volume of it going from a liquid to a solid. So we have done it, but it's how accurate it is. But of course, what we can have an indication of, I mean, we can measure it, so we have an indication. Let us call it an indication. We can also see an indication after solidification if you have this hump at the materials, or if you have actually a cavity, right? So it will give you kind of an indication again if it's expanding or if it's creeping.
But you're going to analyze only this expansion or creeping in the end of the process, but not in the beginning. You analyze that from liquid to solid, not solid to liquid.
Oh, we can do both actually. But it's
Okay.
But we haven't done it actually, I think. No.
Yeah, because each alloy element will have different thermal expansion, and I've been caught on that one.
Yes, yes.
Think about only liquid, solid. Second one, have you thought about additions of alloys that will promote a single crystal to increase thermal conductivity?
To increase the
thermal conductivity.
Yeah, what did you want to add?
Addition of alloys to promote a grain side growth orientation and
we haven't discussed that
solidification.
Yet. We haven't discussed that yet. So it's a too short project. We need more years.
Okay.
Yes.
Last one. With silicon chromium alloys, have you analyzed intermetallic formation?
Yes. What kind of phases we have? Yes. Yes. So what kind of?
Did you analyze this against thermal conductivity? How that would affect in latent heat as well?
We haven't.
Okay. Thank you.